In this video, we're going to look at eigenvalues and eigenvectors. Eigenvalues and eigenvectors. So suppose you have a square matrix A. Again, square would mean like an n by n. So you could figure this could be like an n by n matrix. A non-zero vector say x is an eigenvector and a scalar, usually called lambda, is an eigenvalue if A times that vector is equal to lambda times that vector. So as you can see here, what this means is this eigenvector is such when you multiply the matrix by that vector on the right, that's going to be equal to some number times that vector. So it's kind of an interesting vector, eigenvectors, in the fact that when you have those, the matrix is sort of replaced by a number when you're using that eigenvector. And so geometrically, you can think of it as something like this. If, let's say, if lambda is a real number, and let's say if you have the vector, say, x, what this does, this stretches or shrinks the vector, though it keeps it in the same direction. So you'd have, say, like lambda x here, like this. Or again, because the matrix times x is the same here, when you multiply the matrix times x, you're stretching the vector. Or if it happened to be lambda was less than 1, you would shrink the vector. So once again, if we would look at numbers, say, do this example, consider this matrix 2, 3, 3, 2. And then if we multiply that by this vector, and we go through the multiplications, we'll get 4 minus 6. And we get 6 minus 4. So we end up with minus 2, 2. And now also, let's take the same vector here and multiply it by minus 1. And we get -2 and 2. So notice for this matrix here, this to -2 is an eigenvector with eigenvalue lambda -1, because we can take 2, 3, 3, 2 times 2 -2. That's going to be equal to -1 to -2. Because when we multiply these together, we got -2, 2. We multiply these together, we got -2, 2. So this is an eigenvector associated with this eigenvalue. So again, every eigenvalue is associated with an eigenvector. Now, sometimes the eigenvalues can be 0, but the eigenvector can never be 0. Now, notice a couple other things. Eigenvectors are not unique. So suppose, let me call it, let me call it once again, X is an eigenvector. Then any scalar multiple of X is also an eigenvector, i.e. Cx is an eigenvector for any scalar C. So if you have an eigenvector and you multiply by any scalar C, you still get an eigenvector. So they're not unique. Now, eigenvalues are unique. In other words, if you have an eigenvalue like we did in that last case, -1, if you multiply that by a scalar, it's not necessarily going to be an eigenvalue. So let's do some basic, again, this is probably a review for you, but let's do just some basic calculations for eigenvalues and eigenvectors. Find eigenvalues, eigenvectors of 1, 4, 2, 3. So we have this matrix, and we want to find the eigenvalues and eigenvectors. The simplest way to do that is to, first of all, again, we want to find, as we said before, we want to find the value of lambda such that ax is equal to lambda x. So again, one way to do this, let me go through the steps here. Let's multiply lambda by the appropriate identity matrix. Now, since this is a 2 by 2, we'll use the 2 by 2 identity here. And so we multiply this out, that's going to be lambda 0, 0, lambda. And then the next thing we want to do is take a minus, well, let me do it the other way. You can probably do it, you can actually do this either way. We'll probably do, I'll sometimes change it up. Let me do it this way to start with. You could multiply this out, minus 1, 4, 2, 3, like this. So this is going to be lambda minus 1, minus 4, minus 2, lambda minus 3. So all I did here, this was basically just lambda I minus the matrix A is what this is right here. So we'll do that. And now find the determinant of this. Let me call this equation 1. And let's find the determinant. Remember, that's this times this. Minus this times this. And we're going to set this equal to 0. But let me go ahead and multiply these through first. What is this going to give me? Lambda squared. And do your foiling and add them together. What's that going to be? 4 lambda. And then this is going to be plus 3. This is going to be minus 8. And minus 5. Again, like I said, we want to set this equal to 0. And then we can factor this, lambda minus 5, lambda plus 1. And again, so we're going to set that equal to 0. So it's going to be lambda equal 5 and lambda equal minus 1. So those are the two, these are the eigenvalues. And so once again, just to review how we did that, we took lambda I minus A, worked that, called that equation 1, then found the determinant of that and set that equal to 0. And then factored, find the values of lambda, gave us this. So now to find the eigenvectors, what we do is we're going to go back to this equation here and put in each lambda. So put, and let me do it in this order. Let me start with minus 1. Put minus 1 into equation 1. That's going to give us, when we put that into equation 1, we going to get 1, that's going to be 0. -4, -2, -4. So what I'm doing is putting lambda in here, and that's going to give us -2, -4, -2, -4. And then we're going to multiply this times, sorry about that. So I put -1 in the equation 1, then we'll multiply this by xy. And multiply this out. That's going to give us -2x -4y -2x -4y, and set this equal to 0, 0. And then we want to solve for x and y. The other thing, notice we really just have one equation here because these are the same. So our only equation is -2x -4y is 0. That's going to give us x equal -2y. And so now here's what we have. We have one equation and two unknowns. And what we do here is set one of the variables equal to the parameter. Probably be most convenient, set y equal to the parameter t, like that, where t is a parameter. And then, so what that's going to mean is then x equals -2t. We put that back in here. So therefore, eigenvector is -2t and t. And so what this means, remember, this is a parameter, so you can have any value of t will work. Now, a lot of times what people will do is they'll just pick one here to take a representative eigenvector. They might set t equal 1. So, for example, that. So this is an eigenvector, or any value t, which will give you another eigenvector if you want another one. So again, any scalar multiple, as we said before, that was that principle that any scalar multiple of an eigenvector is itself an eigenvector. So let's go again now. Let's put the other eigenvalue 5 into equation 1. And again, going back to equation 1. And remember what equation 1 was, just at lambda I minus a. So put 5 in for lambda. And when we do that, we'll have like 5 minus 1 minus 4 minus 2, 5 minus 3. That's going to end up giving us 4 minus 4 and minus 2, 2. Once again, just like before, what we do then is multiply this by xy and set that equal to 0, 0. Once again, 4x we get here is going to be 4x minus 4y is 0. The other one's going to be minus 2x plus 2y is 0. Once again, they're the same equation because they're scalar multiples of each other. Because if you multiplied this by minus 2, you would get this. So we only have one equation, and so we'll work with that one equation. We can pick either one here. Let's work with this one here. So minus 2x plus 2y is 0. And we work this out, we end up with what? X equal y. So once again, set y equal t, a parameter. Then x equals t. So again, x equal t, y equal t. So that's going to be tt is an eigenvector. For any scalar t. Once again, for example, if we use t equal 1 is an eigenvector. And so let's summarize what we got for that problem. So summary. Eigenvalue. We said minus 1 was associated with the eigenvector minus 2, 1, or you could use any scalar multiple of this. And then the eigenvalue 5 is associated with eigenvector 1, 1. For the matrix. Let me go back to get our original matrix. That was 1, 4, 2, 3. So again, that's an example of how to find eigenvalues and eigenvectors. And again, you've probably done this before, so I won't do any more examples. Except just to say, just maybe to summarize how we did this. We find lambdas that satisfy lambda I minus A equals 0. Or a lot of times in many books, they'll use it the other way around, or you can solve A minus lambda I is 0. Either one will work. And then, so for example, if it's a 2 by 2, let me do it in this order. If for A equals small a, b, c, d, we're going to have a, b, c, d minus lambda 1, 0, 0, 1. And we're going to end up with a minus lambda, b, c, d minus lambda, and then find the determinant of this. Or I should say, set the determinant equal to 0. Set it equal to 0 to find the eigenvalues. Then secondly, put the eigenvalues into this here. Put each eigenvalue into here, then solve for eigenvectors. Now we have something called the eigenspace, the definition. For a given eigenvalue, lambda, the associated eigenvectors call them, let me just say eigenvectors, along with the 0 vector is called the eigenspace. of lambda. In other words, all the eigenvectors together, remember, you can have any scalar multiple of an eigenvector will give you an eigenvector. So you'll have a infinite number along with the zero vectors called the eigenspace. So these eigenvectors make up a vector space. So from our previous example, we had lambda equal -1, and then all the vectors that were scalar multiples, I think you can use C or you can use T. All vectors say T, or of the form that we had before, -2T and T for all scalars T. Make up the eigenspace of lambda. And I should say, for all scalars, and along with the zero vector, you have to also include the zero vector up here. I should have put that in. Let me just put down here. Also include zero vector. Remember, the zero vector can never be an eigenvector. So when you take scalar multiples here, we actually have to exclude, I should mention before, we have to exclude 0 because eigenvectors always have to be non-zero. So this make up the eigenspace of lambda, maybe specifically lambda -1. Same thing with lambda equal 5. All vectors of the form, what do we have? TT along with the zero vector make up the eigenspace of lambda equal 5. Now let me just go through, I won't go through all the details of this next one, but let me just sort of go through real quickly. If we have a 3x3 matrix, and let me write that a little better. Sorry about that. We'll find the eigenvalues values and eigenvectors of this, and solution. Once again, we're going to take a minus lambda I, or like we did before, you could have also done this as lambda I minus a. And again, this would be this minus 3 minus 5 lambda, 6 minus 6, 4 minus lambda. Once again, we'll call this equation 1. Now, I won't go through all the steps on this, but we'll find the determinant of a minus lambda I and set that equal to 0. And again, I won't go through all the steps. When you do that, you have to do a lot of algebra and so on and so forth. And then you'll end up having this equation. Set this equal to 0. And by the way, these equations, when you have the equation with these lambdas in it, this is called the characteristic equation. And then if we want to factor this, you may have to practice your factoring a little bit. So we'll go ahead and factor this. Again, we factored our characteristic equation. Set this equal to 0. Now, once you do that, you get lambda equal minus 2, lambda equal minus 2, lambda equal 4. Now, just like we did before, we're going to go back and put each of these lambdas back into this equation here. Now here, notice we have a repeat here. So now when you have a repeat like this, you could possibly only have one eigenvector, though sometimes you'll have two. So let's go through this and see what we have. So substitute so put lambda equal minus 2 into equation 1. So put that in here. And what do we get if we put minus 2 in here? This would be minus 2. This would be 3, minus 3, 3. 3 minus 5, etc. That's going to be minus, so it's going to be minus 3 here, etc. So let's do that. Plug those in. When we plug those in, we're going to get 3 minus 3, 3, 3 minus 3, 3, 6 minus 6, 6. Because when we do this down here, we have 6 minus 6, and put minus 2 in here, gives us 6. So do that, and then multiply these out. And again, you could use, like, say, Gauss reduction or some other method to solve this if you wanted to. But let's actually maybe just work with the equations here. Now, first of all, notice these are going to be duplicates. these first two are exactly the same. And go down here, 6x minus 6y plus 6z equals 0. But now notice if you multiply this equation by 2, you'll get this equation. So these are all three the same. So we only have one equation. Let's call it 3x minus 3y minus 3z is 0. In fact, you can even reduce it more by dividing by 3x minus y plus z is 0, like that. Now we have one equation and two unknowns. So we need two parameters. Remember before we only needed one. So let's so we'll need two parameters. So let's set maybe y once again equal to t like we did before, and then maybe have our other parameter s, call it s, z equal to s. So then what does that give for our eigenvectors then? Our eigenvectors, substitute that in here. So we have y equal to t, z equal to s. And then if we solve this, let's say if you solve this here, you would get x equal what to y minus z, or x would be equal to t minus s. So I think once again, now we have two parameters like this. So now let's see if we can separate the parameters. So this is going to give us, you can break this up into two vectors. Let's say you have one with t's in it. T, 0. And then one with s's in it, minus s, 0, s. And then you could factor out your parameters. 1, 1, 0 plus s minus 1, 0, 1. So now once again, you can see we have these scalar multiples. So any scalar multiple of this is an eigenvector, and any scalar multiple of this is an eigenvector. So again, you could say 1, 1, 0 and minus 1, 0, 1 are eigenvectors. Associated with lambda equal minus 2. Now, notice these are different because you can't multiply this by a scalar and get this. So these two are linearly independent. So we do have two distinct eigenvectors associated with that eigenvalue. And again, as I mentioned before, when you have a repeat like that, you could get two eigenvectors, though sometimes you're going to get 1. So let's do the same thing for the lambda equal 4. Put lambda equal 4 into equation 1. So once again, go back to equation 1 here. Put lambda equal 4 in there. And so when we put that in, you're going to get what, minus 3, 3, 3, minus 9, 3, 6, minus 6, and 4. And that's going to be 0 here because we have 4 minus 4. Let's put that down. And just like we did before, let's go ahead and multiply that by a vector here and set this to be 0, 0, 0. And let's see what we're going to get here. So we're going to end up, this time again, you could use Gauss reduction if you wanted to. Or let's see, if there another way, let's see, 3x. Yeah, this one probably would be easier using, like, say, Gauss-Jordan or something like that. And 6x plus 6y plus 0 is 0. And let's see. If we were to multiply, let's say if we took let's see, if we took minus 1 times this one and added it to this one, we would end up getting the same equation. So we took minus 1 times this, and let me show you what I want to do here. Take let's see, let me do it the other way, excuse me. Let me take minus 1 times this. So I'm going to add these two together after taking minus 1 times them. And so this is going to be minus 3x minus 3y plus 3z is 0. And this is going to be minus 3x plus 9y minus 3z is 0. And we'll add those up. Plus 0. Then if we add this to this, this will be eliminated. So that's going to leave us with just these two equations. So again, like I say, I'm sort of doing a Gauss-Jordan without using the matrix. And so if we add this, that's going to disappear. So we're going to be just left with these two equations. Then if we add these, let's say if we added this one to this one, that'll leave us with 3x minus 3y plus 3z is 0. Like I say, if we add this to this, that's going to leave us with a 0 here. And then this is going to give us, what, a minus 12 here. And then plus a 6z here. And we can further reduce these. If we divide this by maybe 3, -3, that's going to give us x plus y minus z is 0. And if we divide this through by, let me divide by -6. That'll give us 2y minus z is 0. So we have, that's all the farther we're going to be reduce it. So we have 2 equations, 3 unknowns. So we're going to need 1 parameter. So let's set z equal to t. It's up to you how you want to do it. Usually what I do is, if with our unknowns, I usually pick the latest letter in the alphabet, set that one equal to the parameter. And if in this case, so I said this equal. And so what is that going to give us? If we put z equal to t here, that's going to give us y equal what to 1/2 t. And then if we put t in here and this in here, it's going to give us x equal minus 1/2 t. And then we bring that to, so it's going to give us a positive t, if I did that correctly. Yeah, and so x is going to end up being, so x is going to end up having 1/2 t. So now the eigenvectors. Use some room. So we said z was equal to t. Y is 1/2 t. X is 1/2 t, like that. So those are the eigenvalues associated, this could be eigenvectors. Again, like I said, or if you want to pull the t out and say it's going to be 1/2, 1/2, 1. So this is the eigenvectors associated with t, excuse me, lambda equal to 4. Yeah. And also going back to the eigenspace deal. So again, for the previous one, we had lambda minus 2, and we had these vectors. So the eigenspace of lambda equal minus 2 is going to be the span of its eigenvectors. And the eigenvectors were 1, 1, 0, and minus 1, 0, 1. Because remember, all scalar multiples of an eigenvector gives you an eigenvector. And then so the span, all the possible linear combinations of these two will give you the eigenspace. And same thing with this other one here, lambda equal 4. The eigenspace of lambda equal 4 is the span of a half, half, and one. Of course, if you have one vector, the span of it is just going to be all the scalar multiples of that. So once again, to just review some things real quickly, you recall whenever you have any square matrix, say 1, 3, 5, 7, minus 1, 2, 4, 7, 5, minus 6, minus 2, minus 3, 10, 12, 16, 4, 8, 7, 13, 20, 21, 11, 4, minus 6, 7. So like for any matrix, the main diagonal is going to be this diagonal right here. That's the main diagonal. It's, again, meaning that center, that diagonal right there. That's the main diagonal of any square matrix, is that center diagonal. And also, we have upper triangular matrices. Would be matrices like, you have like numbers up here. But you have all zeros below the main diagonal. So again, here was the main diagonal. So if it's upper triangular, that means you have all zeros below the main diagonal. Now, above the main diagonal, you could have a mixture of zeros and non-zeros, but the main thing is an upper triangular matrix has zeros below the main diagonal. And so lower triangular matrices, again, they would have zeros above the main diagonal. If it's lower triangular, once again, what all that means is you could possibly, lower triangle, you could possibly have non-zeros in this lower corner, but you have all zeros in the upper corner. Just like up here, for upper triangle, you could possibly have non-zero values in the upper corner, but you have to have all zeros below. Once again, for the lower triangle, some of these could be zeros as well. Now, technically, these could all even be zero. Technically, it would be a lower triangular, but that would also be a diagonal matrix. So remember, a diagonal matrix has all zeros except possibly along the main diagonal. So, 3, 0, 4, 12. So this would be an example where you possibly could have some non-zeros here. So these could either be all non-zero, some of them non-zeros, or all zeros along the main diagonal. But everywhere else, they have to be zeros for it to be a diagonal matrix. Now, what's nice about a diagonal matrix and an upper triangular, lower triangular, so let me just, for upper and lower triangular matrices and diagonal matrices, all eigenvalues are on the main diagonal. So they become very, very simple. So again, this is lower triangular. It's going to have eigenvalues -7, 3, and 4. Same thing if you have an upper diagonal one, or if you, this could be an upper triangle, or if you have a diagonal matrix eigenvalues are going to be -38, 4, and 0. So again, upper and lower triangle matrices are very easy to find the eigenvalues. And one very important thing, this is a theorem, a square matrix A is invertible if and only if all its eigenvalues are non-zero. So it's if and only if, so that means if all the eigenvalues are not zero, it has an inverse. If any eigenvalue is zero, it does not have an inverse. Now we want to talk about similar matrices. And let me give you a definition. Again, you probably had this in a previous course. Again, we're talking about similar matrices. So let A and B be n by n matrices. We say A is similar to B if there exists an invertible matrix P such that P inverse AP equals B. Like that. So you have like a matrix P, and you can, and it has an inverse, if you take the inverse of P, AP, you'll get B. And of course, or you can, do it the other way as well. Let's say if we multiply this side by P, and this side by P, this would be I. And then we would end up having P here. And if you multiplied, PB, if you multiplied this side by P inverse, you get this, and you get that. Or you'd say it this way. Now, of course, since this is the inverse of P, you could call this P and this P inverse. It doesn't really matter. But any two matrices A and B that have this kind of relationship, they're similar. And then if A is similar to B, and this probably varies from textbook to textbook, we write A, B like that. Thus, there's many properties of similar matrices. If A and B are similar, that mean, A similar to B, then we have several properties. The determinant of A equals the determinant of B. And this is very important for what we've been working with. A and B have the same eigenvalues. C, A is invertible, again, has an inverse. if and only if B has an inverse. Or is invertible. So A has an inverse if and only if B has an inverse. And you could, of course, got that from this one here, because if A and B have the same eigenvalues, if one of those eigenvalues is 0, then neither A nor B is invertible. If none of the eigenvalues are 0, then both A and B would be invertible. Another one we have is A and B have the same rank. And another thing that they have is A and B have the same characteristic polynomial. Remember, that's that polynomial when you get when you find the determinant of A minus lambda I instead equal to 0. And so you could, so if you want to actually say it that way, that part, maybe that would just confuse things, but it's going to be that polynomial that you get it when you, if A and B are similar. Now, often we're interested in finding out whether or not a matrix is similar to a diagonal matrix. In other words, are there going to be times when you can find a matrix P to make A similar to a diagonal matrix? And we have like a term for that. We have a definition, and N by N matrix, call it A, is diagonalizable if there is a diagonal matrix D such that A is similar to D. So again, A is called diagonalizable if there's diagonal matrix D again, where D has just non-zero numbers only along its diagonal. And then so i.e., what this in effect means is there is an invertible matrix P such that P inverse AP is equal to D. Now, question is, when can we be sure A is diagonalizable? When can we be sure of that? And so there's actually a theorem that A is diagonalizable if and only if A has n. Again, we're assuming like A is, an n by n matrix. So it's diagonalizable if and only if A has n linearly independent eigenvectors. So if it has n linearly independent eigenvectors, it's diagonalizable. And in fact, in that case, P minus 1 AP is equal to D, where P is like this, and the columns are the eigenvectors. So again, if you have n linearly independent eigenvectors, then it's going to be diagonalizable, and then the P that you have is going to be made up of columns for which the columns are the eigen vectors. Now, previously, we looked at a little while ago, we looked at that one matrix. Recall that A 1 minus 3, 3, 3 minus 5, 3, 6 minus 6, 4 had lambda equal 2 for the eigenvalues, and that had eigenvectors minus 1, 0, 1, and 1, 1, 0. And then for lambda equal 4, we had the eigenvector 1/2, 1/2, 1. So we did that a little bit ago. And now one important thing, again, notice these two are linearly independent. They're not scalar multiples of each other. And now we don't even have to check this one. Whenever you have an eigenvalue and an associated eigenvector, that's going to be linearly independent with any eigenvectors from a different eigenvalue. Like you won't ever have to worry. Now, neither of these are linearly independent. These are linearly independent with these ones. They're never going to be dependent on each other. They're not going to be dependent, let's say. So now we had this, and so what's going to happen in this case, P is going to be equal to the matrix that we have, say right here. It'll be, put these minus 1, 0, 1, 1, 1, 0, 1/2, 1/2, 1, like this. If you put those in, and if you found the inverse, I won't go through the process, but the inverse on this is going to be minus 1, 1, 0, minus 1/2, 3/2, minus 1/2, 1, minus 1, 1. Look at the inverse. Then P minus 1 AP, if you multiply these all out, it's going to give you the diagonal matrix minus 2, minus 2, 4. And so further, notice one more interesting thing. The eigenvalues will be on the diagonal. So remember, our eigenvalues were minus 2 and 4. We see minus 2 and 4. Remember, we did this originally, this repeated, and so this repeats here. And of course, there are several ways you can look at this. We know that similar matrices have the same eigenvalues, and since this is diagonal matrix, its eigenvalues are going to be along the diagonal, so therefore the eigenvalues will be the same and they'll be along the diagonal. Now, one thing about the order, notice how we put these in. And again, you could have put these eigenvectors in any order in P. And I put them in, I put this one in first, this one in second, this one in third. Now this one is related to minus 2. So in the first column here, it was eigenvector related to minus 2. And so that's what happened here. We got minus 2 there. Same, this one was related to minus 2. So we got minus 2 here. The last one was related to 4. Got that here. So the one thing that we talked about before, again, remember when we originally calculated the eigenvalues here, we got minus 2 and minus 2. So we had 2 of them. So whenever you have 2 eigenvalues the same, you could possibly have 2 eigenvectors, or you may just have 1. You're always going to have 1 no matter what. But if you have repeats, you could have 2. If minus 2 had showed up 3 times, we had minus 2, minus 2, minus 2, then we could possibly have had 3 eigenvectors, or we could have 2 eigenvectors, or we could have 1 eigenvector. So that relates then to algebraic multiplicity. And we'll talk about that next. Algebraic multiplicity of an eigenvalue is simply the number of times it appears. So in the case that we had here, like I said, when we originally did this, we said that we found we had -2 and -2. So the algebraic multiplicity of -2 would be 2. Now, 4 only showed up once when we solved the characteristic equation, so its algebraic multiplicity would just be 1. So, for example, suppose a matrix has eigenvalues. Let's say lambda is equal to 3. Let's say -1 repeated. And let's say 5 repeated 3 times. So lambda equal 1 has algebraic multiplicity equal to 1. Now, -1 has algebraic multiplicity equal to 2. And 5 has algebraic multiplicity equal to 3. So now geometric multiplicity of an eigenvalue is is technically the dimension of its eigenspace which, remember, all that means is that would be the number of linearly independent eigenvectors associated with that eigenvalue. So once again, looking at that example that we did a minute ago, remember lambda equal -2. It had 2 linearly independent eigenvectors. So its geometric multiplicity was 2. Now 4 only had 1 linearly independent eigenvector. So that means its geometric multiplicity is 1. Now, as I said before, if you have, again, duplicates, if you have duplicate eigenvalues, you may or may not have more than one eigenvector. So let's do an example to kind of show. So suppose a 7x7 matrix has eigenvalues let's say 2, 2, -4, 5, 8, 8. Now, without actually knowing the eigenvectors, we can figure out what the possibilities are. So again, you have eigenvalue. Let's look at each of these. And we have the algebraic multiplicity and geometric multiplicity. And so for, let's say, the eigenvalue 2, remember it repeated twice, so the algebraic multiplicity was 2. Now the algebraic, now you could have one eigenvector, or you could possibly have two. Without actually doing the calculation, you're not sure. So this is going to be 2 or 1. You always have to have at least one eigenvector. So your geometric multiplicity for any eigenvalues has to be at least 1. But in this case, since we have the duplicate, and our algebraic multiplicity was 2, you could possibly have 2. You won't know without actually doing it. Now for the next one, -4, its algebraic multiplicity was 1, and the geometric multiplicity, remember, it can't be more than this, but you always have to have one eigenvector. So that's the only possibility there. Now the other one for 5, the algebraic multiplicity is 1, only appears once. And once again, you're always going to have one eigenvector. And you can't have any more since you only had one. You didn't have any repeats here. Now for 8, the algebraic multiplicity is 3. So you could possibly have 3 eigenvectors, or maybe only have 2, or you could possibly only have 1. Now notice, this is very important. Notice if the total algebraic multiplicity equals the total geometric multiplicity, then we will have n eigenvectors or in this case, 7, since our n is 7. So if it happens to be that, like they're equal, so like here, for example, if you ended up having 2 here and having 1, of course, here, and let's say you had 3 here, you would end up having 2, 3, 4, 7 eigenvalues, eigenvectors, and 7 eigenvalues, including the repeats. Now, in that case, if you have that case where they are equal, the matrix will be diagonalizable. Because remember, if you end up having 2 eigenvectors here, they're going to be linearly independent. And then remember, from eigenvalue to eigenvalue, its eigenvectors, they're always linear independent of each other. And if you have all 3 here, these are going to be linearly independent. So if you have like what's called a full set of eigenvectors, which again means you have the n total, where n is the dimension of the matrix, then it will be diagonalizable. So that kind of leads us, notice in the case, therefore, for matrix, excuse me, for a matrix, let me redo this. So suppose matrix A has eigenvalues And let me say this is say a 9 by 9 matrix A has eigenvalues, say 13 minus 6, 4, 12, 8, 42 minus 20, 6, and 9. Notice there's no repeats. So therefore, for each eigenvalue, the algebraic multiplicity is going to be 1. And the geometric multiplicity is going to be 1 for each one. So they're going to be equal. So that means, again, if they're all distinctive, if they're all different, the eigenvalues are all different, then you will end up, in this case, with 9 linearly independent eigenvectors. And that's equal to the size of the matrix. So, therefore, A will be diagonalizable. Now, just a couple final things here. So for any diagonal matrix, say D, let's say we're D, let me just pick, say, a 4 by 4, A, B, C, D. Again, it's a diagonal matrix, so there are zeros everywhere. Now, again, remember, for most matrices, squaring the matrix, is kind of tedious, but for diagonal matrices, you can take it to any power, and really for any integer power. And all you have to do is take the elements along the diagonal and take those to that power, like that. So, for example, if you want to take 2, 0, let me take a small matrix here. If you want to take it to the 6th power, all you have to do is take the diagonal elements to the 6th power. Of course, you can't normally do that with any old matrix, because you can't just take the individual elements to the power. You have to actually we'd have to multiply this 6 times out in the normal case. But if it's a diagonal matrix, this is all you have to do. So this leads also to something very interesting. note if A is diagonalizable, with say something like this, P minus 1, a P equal to D, like this. Then, of course, remember, we can write this way. If we multiply on the left by P and on the right by P inverse, we can also write this way. And now let's see what happens if we square A. Let's say if we square this, and let's say if we square this here. Now, what does this mean? So if we square this, is going to be P D P minus 1, this times itself, P D P minus 1 here. And again, this is the identity. And so this is just going to end up, in effect, going away. And so this is going to be P D squared P minus 1. So if you square A, you can calculate that by doing P D squared P minus 1. And you can go through the same process and show that A to any integer power is going to be this for any integer n greater than or equal to 1. So for a diagonalizable matrix A, if you know that the matrix is similar to, and you want to take it to any power, any integer power, all you have to do is take P times this and then take this to that power. Remember that taking diagonal matrix to a power, as I said just a minute ago, it's very easy. And so once again, let's look at that same example that we've been using. Find 1 minus 3, 3, 3 minus 5, 3, 6 minus 6, 4. Let's say if we cube that. And then previously, we found that P, when we put the eigenvectors here, was this. And then we said P inverse like this. And then we also found previously the diagonal matrix was this. And then so if we want to find this cubed, all we have to do, so if we call this our matrix A, then as I said before, A cubed is simply going to be P minus 1 D cubed times P, or excuse me, I should do it the other way, P D cubed P inverse, like this. And then if we cube this, which means cubing this, that's going to simply be P. And then they'd be cubing this. What's that going to be? Like minus 8. Minus 8. And what's that? 64. The inverse. And then if we put this in here and this in here, we end up getting 28 minus 36, 36, 36 minus 44, 36, 72, minus 72, 64. So again, it kind of illustrates how you can use the diagonal matrix to find powers of A. Just take that diagonal matrix, that power, and gives you this.